Welcome back, students. Welcome to the lecture on signals and systems, lecture series on signals and systems. In this lecture, we are going to study about several elementary signals which play vital role in the study of signals and systems. These elementary signals serve as the most serve as the basic building blocks for the construction of more complex signals. In fact, these elementary signals may be used to model a large number of physical signals which occur in nature too. These elementary signals are sometimes also called as standard signals. The standard signals that what we are going to discuss in this present lecture are, so there are variety of elementary signals, but however, I would like to start with a unit step signal. A unit step signal. A unit step signal is an important signal which is used for analysis of many systems. The step function is that type of elementary function which exists only for positive time and is zero for negative time. It is equivalent to applying a signal whose amplitude suddenly changes and remains constant forever after applications. So let us mathematically define this particular signal. Unit step signal is denoted with u of t, and mathematically as defined, it is equal to unity for all t greater than or equal to 0, and it is 0 otherwise. That is for t negative, t less than 0. If a step function has a unit magnitude, then it is called unit step function. The usefulness of this particular function lies in the fact that if we want a signal to start at t is equal to 0, so that it may have a value of 0 for t less than 0, we only need to multiply this given signal with unit step function. A unit step signal can also be used as a test signal because the response of the system for a unit step reveals a great deal about how quickly the system responds to a sudden change in the input signal. And from this above equation that u of t, we can observe that when the argument t in u of t is less than 0, then the unit step function is equal to 0. And when the argument t in u of t is greater than or equal to 0, it is equal to 1. And it can be represented in this form by using a graphical representation. You can see this, the unit step function can be represented that it is equal to 1 for t is equal to 0 or greater than 1, greater than 0. This is generally represented with u of t, and this is the time axis, and you could see that for all t greater than 0, greater than or equal to 0, it is equal to 1, and for t less than 0, it is equal to 0. It is equal to 0. And in the same way, you can also define a discrete time unit step signal, which is given as u of n is equal to 1 for n greater than or equal to 0, and it is equal to 0 for n less than 0. And the graphical representation for this discrete time version of unit step sequence can be taken as u of n, and this is your n axis, the time axis, and it is equal to 1 for all n is equal to 0 and n greater than 0. It is equal to 1 for all n greater than 0 and equal to 0. So this is how we generally consider a unit step sequence. And as said, this has many practical applications. And now let us move to another function called as a unit ramp function. The continuous time unit ramp function r of t, generally we represent this ramp function with r of t, and it is given as that function which starts at t is equal to 0 and increases linearly with time, and it is defined mathematically as r of t is equal to t for t greater than or equal to 0, and it is equal to 0 for t less than 0. Therefore, this r of t can be represented in terms of unit step as t multiplied with u of t. U of t is a positive sided signal, that is a one-sided signal which exists only for positive values of time. Therefore, when t is multiplied with u of t, it exists only for t greater than or equal to 0. This is how you can say, you can represent the unit ramp function in terms of unit step function. The unit ramp function also has a unit slope, and it is a signal whose amplitude varies linearly. As shown in this particular figure, you can see that unit ramp function has a unit slope, and that means wherever you take the value of t, that r of t, it will be equal to t, and it is a signal whose amplitude varies linearly, and it can be obtained by integrating the unit step function also. That means that a unit step signal can be obtained by differentiating this unit ramp signal too. So now I can represent that r of t is equal to integral of u of t dt. When I integrate u of t over 0 to some infinity, we'll be getting it as integral of 1 dt, which will be equal to simply t. This is how you can see that this, since u of t exists only for t greater than 0, t greater than or equal to 0, therefore r of t also is equal to t for t greater than or equal to 0. In the same lines, you can also write that u of t is equal to the derivative on ramp signal, that is d by dt of r of t. Okay, the derivative on the differentiation on your ramp signal gives us the unit step function. Okay, I have already shown you this the graphical representation of a continuous time unit ramp signal. In the same way, we can also define a discrete time unit ramp sequence, which is defined as r of n, which is equal to n for n greater than or equal to 0, and it is 0 for n less than 0. Okay, and similar lines you can also represent r of n as n into u of n. If you would like to see the graphical representation of a discrete time unit ramp signal, it would be something like this. At 0, it will be equal to 0, the amplitude is 0. At 1, it is equal to 1. At 2, it is equal to 2. At 3, it is equal to 3, and so on. That means this increases linearly. Therefore, this is just a discrete time version that what we have seen earlier for the continuous time version, and it is equal to 0 for all t less than 0 too. Okay, same as in that case of continuous time also, it is equal to 0 for t less than 0. That's all for this lecture.